Hi guys, welcome back to part 4, example 2. So let's get straight into it. We have a situation where the builders has installed a different beam size to what was nominated by the engineer. So initially the beam size of B1 was nominated to be 2 240s by 45 F17 KD hardwood. Now B1 is a floor beam where it supports floor joists, upper wall loads, and tiled roof loads. After the building surveyor conducted a frame inspection, he noticed that the guys on site installed a single 240 by 45 F17, which and that is also a KD hardwood, which kind of left a 45mm overhang, but then later on they laminated a single 190 by 45 F17 B1A from the outside under that overhang. Now the beams were laminated together with 2 rows of number 10 screws to the external side at 400 centers, and the screw shank diameters for number 10 is generally 4.88 millimeters. There is also a 50mm edge distance and a 50mm end distance to the center of the screws. The builder also stated that they used an 80mm long screw, which kind of leaves a 35mm penetration depth into beam B1. Okay, now it's time for the engineer to justify the fixing details, and if it's not satisfactory, then we need to provide a rectification detail. Some may ask, how do we know exactly how long the screws are? Well, most of the time I recommend the building surveyor to ask one of the guys out on site to remove a screw from the middle of the beam, especially if it's a simply supported beam where shear stress is minimal in that area. And then when you take the screw out, you can measure exactly the length of the screw. And I think this is probably a reasonable way to make sure. Okay, here we've shown an elevation and a detail of the beam fixings that was done on site. Here we have that 50mm edge distance and the 50mm end distance. The edge distance seems to be okay when you first look at it, as per the code requirements, AS 1720.1, the timber framing code, the timber design code. Table 4.8. So please refer back to that if you are using the Australian standards. I think the maximum, the minimum edge distance that you need is 5 times the shank diameter, which is 5 times 4.88, and that would be 24.4. But we have 50mm here in this case, and the end distance, the minimum distance for that is 10 times the shank diameter. So 10 times 4.88, that'll be 48.8 millimeters. And we have 50mm. So yeah, that's good so far. So we don't have to change anything in that sense. All right, now to the beam loading and fixing information. Let's have a look. The length of the beam is 2500. The factored loads for strength, the UDL loads, is 15.5 kilonewton per meter, and the worst case scenario in this case was 1.2 G plus 1.5 Q. That's the worst loading combination for this particular case. The timber joint group is JD3, that's for KD hardwood. The single number 10 screws were used, and that's 4.88 millimeters in shank diameter. And for the loading combination of 1.2 G plus 1.5 Q, and also the loading duration factor K1, the factor for that was 0.69. Now that was also the worst case scenario for the screws, and I think we missed one. So the single the actual capacity, the capacity for the screw. So each screw is also given to us here of 1.51 kilonewton. Okay, so 1.51 kilonewton is the capacity per fixings, and that was based on the duration factor K1 of 0.69. Right. For a single 240 by 45 F17, the vertical shear force failed by approximately 12%. Okay, V star was greater than 5 VU. The moment capacity failed by about 7%. The long-term deflection, which is the most critical case here, the long-term deflection failed by about 40%. Maybe it's a little bit less than that, but it's about 40%. Now, the common question that one may ask is, what if a single beam, what if a single beam 240 by 45 was satisfactory in strength and serviceability? Can I leave it as it is? Or can I just maybe use a nominal nailing plate with nominal fixings to the outside? That's a very valid question. Now, before we answer that, we need to kind of ask ourselves follow-up questions, okay? Does the upper wall carry any studs which supports a girder truss load, or maybe a large point load? So you need to check for that. If so, then, we probably would need to take the eccentricity into account. If we assume a conservative point load at the edge of the plate, then we will need to check if it will come out at the ends or not. So check if one possible solution is to provide additional vertical screws to hold down the plates. We could also put hoop iron strap as well over. We can put the hoop iron strap over the plates between the blockings, and then screw that over, and that we can probably hold down the plates using that technique as well. So there's different ways we can hold the plates down. So you'd need to check for the uplift of the plates. And if we have failure, like local failures under the point load, we can sometimes put soldier blocks, individual soldier blocks, and we can screw that into beam B1 underneath the point load. So that's another alternative that we could have looked at as well. So yeah, ask yourself these questions about the upper wall loads. We can also ask the builder for a girder truss layout, the trusses layout, and you can see where all the loads are located. The second question that you may need to ask yourself is the bracing condition of this wall. How is it braced? Is it the plywood, cross bracings? What is the wind pressure acting? What is the wind rating? The vacuum force? I mean, at the end of the day, we need to make sure that the vacuum forces in the wall above is transferred somehow right to the ground floor, right to the slab. So it will go through the plates, and then through the blocks as well, and then through the beam, and then right through the walls below, and finally to the slab. So you need to consider the load path of the wind pressure as well, and have you considered that in the overhang? And the third question you might ask, and that's the final one, you may want to ask is, where in the NCC, in the National Construction Code, what does it say about the tolerance that has been allowed? There's also a guide to standard and tolerance handbook that you can refer to. You might be able to download it for free as well from the internet. So go back to that and see what it says about the tolerance of the overhang. Now, if you have gone through this whole checklist and everything is okay, then I cannot see why we can't use a standard nailing plate, with nominal fixings. So yeah, now let's have a look now at the beam model. We have a 15.5 kilonewton per meter, and that's factored, UDL on the beam. We could have also taken this beam model with a series of point loads from the joists and from the upper wall loads, but I thought I'll simplify this problem and just take everything as a UDL load. In general, most of the time, we see engineers, and this is the right way of doing it, is taking the UDL from the self weight alone and then series of point loads from the joist and from the upper wall loads. Okay, so now let's obtain the reactions, FYA and FYB. Now for this case, it would simply be 15.5 times 2.5, and that'll be 38.75 kilonewton, which is like a virtual point load in the middle of the beam. Then divide that by 2, which will give us 19.375 kilonewton. Now step 1, let's work out the shear force. Now for this example, we will work out the shear force and the shear flow as well as the fixing required based on the conservative value of the maximum shear force, which is 19.375, assuming that the shear force is right through the entire beam, like a point load, right through the entire beam. And then we will also look at the fixings required using the average, a non-conservative approach, if you like. So we will use the average value of the shear force. We will do it both ways. Okay, let's have a look. So we have the shear force diagram here. Now the second step is determine the first moment of area Q. Now the geometrical centroid of this whole section now, which is the 190 by 45 and the 240 by 45 together. We work at the centroid. And from the bottom of the section, it is worked out to be 131.05 millimeters. So Y bar, which is the distance from the centroid of that hatched area to the geometrical centroid of the whole section, is 13.95 millimeters. So simply that's 240 minus 131.05 minus 95, which is half 190, and that will be 13.95 millimeters. A bar is simply the hatched area, and that is 190 times 45. Okay, so the first moment of area Q is the sum of A bar times Y bar, and that will be 119,272.5 millimeter cube. Okay, look, I might do another video on how to calculate the geometrical centroid as well as the second moment of area. I know some of us, we forget that. Even I myself sometimes forget. So I might do a separate video on that so you can refer back to it. Let's have a look now. The third step is determine I, the second moment of area, around the major axis this time. A bit different than the last example, but now the beam is bending around the major axis. And I is 8.05 times 10 to the power 7 millimeters to the power 4. I was thinking about this. I have a question for you guys. Imagine, just for an example, for argument's sake, say we have a similar situation where we are joining two concrete beams together with dowel bars. What value would you use for I, for the second moment of area? Now have a think about it. Would it be the uncracked second moment of area or the cracked second moment of area? It's a little bit different than timber. Well, the simple answer to this question would depend on the value of the applied moment in respect to the cracked moment of the concrete. Now, the cracked moment of the concrete would generally include the tensile stress capacity of the concrete minus, any shrinkage stress. So we would need to look at the whole beam, the bending moment in the whole beam, and check which areas of the beam that's cracked and uncracked and use the relevant values. So in areas that the beam is cracked, we use I cracked, and in uncracked, we use I uncracked. I think I got excited too quickly for this, so I might leave it for a different example because it is a little bit different than timber beam, than working, the shear flow and shear stress for timber beams. Okay, let's get back into it. Where are we? Now the fourth step, work out the width or thickness T, which is perpendicular to the shear flow. In this case, the shear flow is running into the page in this plane here between the two beams. So yeah, so here is also I've shown a top view of the beams and the direction of the shear flow. So in this case, the width or the thickness that's perpendicular to the shear flow would be 190 millimeters. The fifth step is work out the shear stress and the shear flow. Shear stress, VQ over IT, and that will be 19.375 times 1,000, converting everything to Newton, multiplied by Q, the first moment of area, 119,272.5, divided by the second moment of area, 8.05 times 10 to the power 7, multiplied by the width of 190. That will be 0.151 MPa. The shear flow, you simply multiply the shear stress by the width. So that will be VQ over I, and that will give us 28.7 Newton per millimeters. Okay, in step 6, we can determine all the capacity and the spacings required. And this is a conservative approach, assuming a constant shear force through the beam. So the total length, the total longitudinal force in this case, so we have a beam of 2.5 meters, so that'll be 2,500 millimeters multiplied by 28.7, which will give us 71767.2 Newton, and that's equivalent to 71.76 kilonewton, which means basically 38.88 kilonewton, right, is going to one direction to the right and the other one is going to the left. Okay, so you're sharing the shear force between half the beams. Okay, in total it will be 71.76, but one half of the beam will take 38.88 and the other half will take 38.88, and in the middle it will be 0. Now this is so obviously this is based on a continuous maximum shear force of 19.375, and that's a conservative value. Therefore we need to distribute the screws in the entire beam to withstand 71.76. Now the capacity of one screw was given to us as 1.51 kilonewton, and we have 4 rows. We are proposing 4 rows in this case. So two rows either sides. There's 2 rows existing already from the outside, so we want to put another 2 from the inside. Okay, so therefore 71.76, divide that by 4, that means 17.94 kilonewton per row. Okay, therefore we need 17.94. If we divide that by the capacity of one fixing, which is 1.51, we will have 11.88. So obviously we will round that to 12 screws for each row. So we need 12 screws for each row throughout the length of the beam. Therefore, to find the spacings, we say 2,500 divided by 12, and that will be 208 millimeter centers. And we can assume, maybe round that down to 200 centers and be conservative. Okay. But like I said, we currently have number 10 screws at 400 centers on one side only, which is not enough according to the conservative approach. So to be absolutely conservative, we need to direct the builder to provide additional screws between the existing ones. as well as screws at 200 centers on the other side, and that will be staggered. Okay, now this is, maybe it is a little bit too much. Now let's have a look at the other approach. We can determine the capacity and the spacing required using a non-conservative approach, okay? So, to save the day for everyone, here we have another elevation of the existing. We've shown the existing beam again and the fixings at 400 centers. And yeah, and I've shown here the shear force diagram as well, just under the elevation, so you can see what's happening. Right, now the corresponding average values, if we take the average value of that shear force, it will be 9.7 kilonewton, okay? That's approximately at 625, obviously halfway, 625 millimeters. The average shear flow would work out to be 14.37 Newton per millimeter, and the average total shear force is 14.37 times 2500, and that would be 35925 Newton, which is 35.925 kilonewton. I mean, half of that initial value that we worked at before. Now for 4 rows of screws, we say 35.925 divided by 4, and that will be 8.98 kilonewton per row. The number of screws per row is 8.98 divided by, again, the capacity of one fixing, which is 1.51, and that will give us 6 screws, okay? Half of the previous values. I just thought I'll do it step by step so you can see what I have done, if you want to justify it yourself later. So therefore, to find the spacings, 2500 divided by 6, it will give us around 416 millimeters, right? So in this case, it will be ideal to put the first screws spacings at the ends at 200 centers, maybe just leave them at 200 centers because this is where maximum shear stress is. And then the rest of the beam space it out 400 centers. So this way, you know, everyone can sleep at night and we all did the right thing. And I'm sure the builders would be happy. I mean, leaving everything at 400 centers from one side, and all they need to do is from the other side shoot it in, or screw it in at 400 centers. And we can use the same screw size of 10, number 10. Yeah, and here we have the rectification detail showing the spacings at 200 centers, and then at the ends over here, and then 400 centers in between. Now, a common question is asked, what happens at 0 shear force? Okay, do we need any screws? Well, technically, no, because at 0 shear force, you'll have zero shear stress, and you don't need that. But we have, every code has minimum spacing requirements. So as per if you refer to the code, you need minimum spacing requirements. I remember from AS 1684.2, the minimum spacing requirement along the grain is 2 times the beam depth. So you need to check that. I think it's 2 times the beam depth. So, you know, if the beam depth is 300, you need 600 spacings. Actually, that's maximum. So yeah, you do need minimum, whether it's 10 times the shank diameter. That's right, 10 times the shank diameter is minimum, and then the maximum, according to 1684, is 2 times the beam depth. So yeah, don't quote me on that, just double check that according to the code requirements of your own country that you're working from. So let's, I think this is it, really. I think that sort of ends my story about shear flow and shear stress. So yeah, and we've found the spacings of at now 400 centers. Now in the next video, I have another example that I'd love to show you. We will look at a 4 meter long floor beam which resists floor loads, floor dead loads, and live loads. B1 was given to us as 3 laminated beams that kind of takes the shape of, it takes a very similar shape to a T-beam. It looks like this, okay? Very interesting example. And again, we need to work out the size of the spacings and the fixings required. And this time we will use bolts. So please stay tuned, and I hope that you can enjoy this one as well. So yeah, please, if you've enjoyed this video and found it useful, please share, like, and subscribe so that others may also learn. Until next time, we hope you have a great afternoon.